we have lost what I have presented until now, but maybe it is recorded separately. All right, so I was speaking about vapor. Vapor are real gases that are not far from the condensation state. So,
Ar trebui să vedem ceva.
Yes, excuse me. Interesting meeting. Please tell me immediately if something is wrong. You can see now. Yes?
Yes.
Okay, excellent. So, what about perfect gases and real gases? I wanted to tell you that, let me see. Yes, okay, it's recording. We will not study this vapor in this lecture because we don't have time, unfortunately, but you will meet them in another lecture, I think in thermal machines. So there you will study also steam turbine, gas turbine, and so on. So perfect gases versus real gases. So let us see what belongs to each of them and what does the difference between them. Of course, the definition of the gas I do not have to tell you because it's a gas, it's a substance in gas phase, of course. But we have to mention these conditions of temperature and pressure, which is far away from liquefaction. So we push away a little bit the gas from this part where, from these properties or values of temperature and pressure where we can have phase change. And also, in order to introduce the perfect gases, we have to look a little bit in this field of kinetic molecular theory, which helps us sometimes to introduce properties, but we won't enter in detail because it's more complicated and not needed for your basic knowledge. But we have to mention that in this theory, a hypothetical gas, hypothetical means that, of course, it does not exist in nature, is introduced or is defined and is named ideal gas. This ideal gas is based on 4 hypotheses, namely perfect spherical molecules, elastic molecules, lack of cohesive forces between molecules, so we don't have this problem of attraction, and also negligible volume. So for this ideal gas, there were some simple laws that were introduced based on experiment. And they are called ideal laws. Now, when we are looking to the gases in nature, the experiments that were done show that with good approximation, they follow this simple law, but only in particular conditions, namely small and medium pressure, medium and large temperature. And these gases will be named perfect gases. So we can already call what we introduced for ideal gas as perfect gas laws, and we will use them like this. Furthermore, if we look to the temperature and pressure variation range in thermal machines, we will see that for usual gases that we have in these machines, oxygen, hydrogen, methane, nitrogen, air, and so on, CO2, carbon dioxide, using this perfect low gas leads to error less than 4%. So keep in mind this 4% that is considered technically acceptable. So in this case, we are now allowed to discuss about perfect gas laws, which has some advantages, mainly of simplicity and then easy to handle. What's happening if the pressure has high values and the temperature low values? In this case, if we try to apply the perfect gas laws, we will have huge errors. So in this case, we actually go back to real gases. We call them, in these conditions, we call them real gases. And we explain this different behavior, these errors, because two of the hypotheses of the ideal gas, which were also a little bit transferred to perfect gas, are not anymore valid. Namely, the cohesion force between molecules cannot be neglected, as well as the molecule volume. All right, so I think that now you are a little bit more oriented on a thermal working fluid in thermal machines. What means ideal gas, what means perfect gas, what remains for real gas. Actually, real gas, as I mentioned, can contain all gases, but for particular conditions, they become perfect gases or only perfect gases, because we agreed that the ideal gas does not exist. It's only a hypothetical one. All right. So for these gases, perfect gases so-called, we will introduce the laws, which are 6 or 7, I don't remember now, which will be used, will be the basis for all our application, numerical application. You see here the first one, Boyle and Marriott law. Okay, Boyle and Marriott law did experiments with a vacuum chamber, and they found some particular behavior of gases when the temperature was kept constant. Now, you see here 2 years. Yes, the distance is 14 years in between. What means this? There is one person, there are 2 persons, 2 researchers, or what do you think? Well, we don't have an opinion. No opinion. Do you hear me?
Yes.
Okay, you lost your voice or you are thinking longer than necessary?
I'm having problems with my connection. Sometimes
so it's
it
not
cuts off.
I see.
Did you ask
okay.
anything?
Yes, I ask if Boyle Marriott is one person or 2. In your opinion?
2 persons.
2 people.
2.
2. Why 2? Cela.
Probably Boyle started the law and then Marriott added something to
I
it.
did something. Yes, it would be an idea, but it's not what happened. Actually, looking to the year 17th century, yes, there were no means of communication, no journals, no conferences, nothing. So each researcher worked in his own small group. And it happened that they discovered the same thing in different years. And even if Marriott discovered later, due to the fact that they could not communicate, so it was not something that was stolen, they are mentioned, both of them, as discovering this law. So that's why I mentioned these 2 years, to see that science was not an easy task at that time. So what did they find? At T constant, they found that the absolute pressure of a perfect gas is inversely proportional to their volume, which we already used in the application last week, this law. This could be written PV equal constant, or when we apply to a process from an initial to a final state, it will be expressed as P1 V1 equal to P2 V2, or in the corresponding form for 1 kilogram of gas, we will use the specific volume that we also introduced last time, with the remark that the specific volume is equal to the reverse of the density. And in this way, we could also express, I didn't add this expression, P equal to density. Actually, this form is not available because it will be P over the density. It's constant. But it's not usual in this, or it's not representative for this statement. That's why I didn't add it. Now, looking to the law, PV equal constant, it means that we want to look to the graphical representation in PV diagram. We have as curve P in ordinate and V in abscissa. So P is constant over V. What mathematical curve corresponds to this? Let us go back a little bit to mathematics. Well, P or Y equal to 1 over X, for example. The constant could be whatever. Curve. Well, Mustafa, you are very quiet today. Are you with us? No, you are not with us. Okay. So, no mathematics? P equal to constant over V. Okay, if you have no idea, this is it. In normal conditions, I would have sent you to internet to look for this representation, but in these special conditions, I have to give it to you. So, P equal to constant over V gives you a symmetrical hyperbola family, which means that they are equally, symmetrical, means that one point is at equal distance from the two axes. And as you see, when the temperature rises, the hyperbola moves away from the axis origin. Now, a theory question to the exam could be, I'm giving you two processes or a cycle, and I ask you to put in hierarchic order the temperatures. Doesn't matter what process are involved, but using this Boyle-Marriott law, you can solve the problem, because you will place the isothermal lines corresponding to each state, and you will see which one is closer to the origin. This will have the lowest value, and which one, and then how they are placed in between the lowest temperature and the highest temperature, which will correspond to the hyperbola, which is far away from origin. So this could be, for example, and this way you can use also this law, not only for the mathematical expression that you apply for an isothermal process. The second law will take another property that will be kept constant, and the name of Gay-Lussac is related to this law. Look to the year and to the distance between these two laws. So more than 130 years, which means that you see the research in this field started around 17th century, and the thermodynamic laws were stated only around 1850, and from there was a huge development of thermodynamics. All right, let us see what found Gay-Lussac. He made experiments keeping the pressure constant, and he found that the volume of a perfect gas is proportional to its temperature. So now proportional, we will see a little bit later the law, because now it's the moment to answer. I don't know if Miruna or Maria asked me last time where from comes this 273.15. So now you will see the demonstration using this dilatation coefficient at P constant, which was found by Gay-Lussac having this value of 0.00366 degrees to minus 1. So the dilatation coefficient actually shows the volume variation in time divided to the volume at 0 degree, when the pressure is kept constant, as I mentioned before. Now, if we approximate, we pass from we pass to finite values here. We will have delta V, V0, and T. So we may use this expression to determine alpha. Now what follows is the observation that delta V from here, it's alpha V0 T. And otherwise, we know that the volume variation, it's the difference between the final volume and the initial volume. So combining these two expressions, we will get dependence on the volume, volume variation depending on the volume in the initial state. This 0 generally means 0 degree, and the presence of this dilatation coefficient. I think that this law is not a singular one. You have found it for several properties, and we just cite few of them, that some of them will be used in this lecture, some of them in other lectures. For example, the length of thermometric device based on dilatation will follow this law. The length is L0, 1 plus alpha T. If we look to the conductivity, when you will study heat transfer, it will be as well a lambda 0, 1 plus beta lambda T. I put it here beta because alpha in heat transfer means something else. The density follows the same law, or the specific heat. In this case, the specific heat takes into account only the linear form without C0. It's only the linear dependence on temperature. Now, of course, that this alpha dilatation coefficient, it's not the same for volume as for length, as for density, and so on. So each property has its own coefficient that is used in this dependence. And these coefficients generally are known, the values of them from the literature. Now, how can we use further this expression and the value that was derived? Making the volume 0, we will get from here, so if the volume is 0, we remain with this parenthesis equal to 0, from which T will be minus 1 over alpha. So if we do this, the replacement of alpha value, we will get 273.15. So you see, it's not a number that Gay-Lussac dreamed or found different else, or it was just in his imagination, but it's something that derived from experiments. Now, this expression actually help us to use only the value of alpha, which can be also expressed by 1 over 273.15. So in these conditions, going back to the initial expression that we used and replacing alpha, you see from here, we change between them alpha with 273, minus sign will be lost. So we have this parenthesis where when we express it, we will get also the expression of the passage from degrees centigrade, temperature in degrees Celsius, to Kelvin. So we have now already two gains, the law and the temperature on the absolute scale. So this allows us to do a step further and to express the law V over V0 T. Yes, this is T, capital T, over T0, which means that the law states V over T is constant, and for n kilogram, of course, enters the specific volume. From this V over T constant, when you apply to a process, of course, you will use it as V1 over T1 equal to V2 over T2. So with this and with the graphical representation, we have a complete idea on Gay-Lussac's law. Now, in this case, as you see the law, V is constant times T. So we will get straight lines, yes, with different, starting from the same point. If we represent in volume and absolute temperature coordinates, the origin will be 273.15. If we try to use the temperature in degrees centigrade, which is not quite, or it was used at that time, this single same point is situated to minus 273.15. So it's a question of origin due to this value that enters in the expression of absolute temperature. Now the pressure, you see the curves corresponding to higher pressure comes near the origin axis when P increases. It is the reverse compared to the temperature that were moving away as temperature rise. Now it's the reverse. So you have to consider this different behavior when you work with graphical representation of processes. It can be explained connecting the volume at different pressure, same volume, and to see what's happening with temperature, logically explanation. Okay, the last law with a constant parameter, it's the Charles law. The year it's around 1802 as for Gay-Lussac, but I didn't mention it anymore. And it stated that at V constant, we have a parallel. That's why I'm telling you with Gay-Lussac, I am mentioning Gay-Lussac. This time the absolute pressure is a function of temperature, direct proportional to temperature, and with the corresponding application to a process. Now, I will not insist here, the graphical representation, it's your contribution if you want to complete it. It could be a question for the theory exam, for example, so you can try to solve it before. The fourth law, we are mentioning it now, but we will use it in the next chapter, the first law. What states Joule's law? It deals with the internal energy, which for a perfect gas, it is function only of temperature. We will see how this will help us when we will discuss about caloric state equation. But there is a small interval until then. And we arrive with this at the thermal equation of state. Again, one of you were interested last time to see where from comes this form that we were used, PV over T, it's constant, because we mentioned only this connection of the three parameters that characterize a state by no matter what function. In order to do this, we consider 1 kilogram because it's easier to derive the equation of perfect gas. Following one process, we will say, between an initial and final state, characterized by P1, V1, T1, and the same for the last state, the final state, but this process is done in two successive steps. It means that we do not have a direct passage, but we pass from an intermediate state, splitting the process actually in two processes. As you see in the figure, it means that we have a T constant process from 1 to alpha and a P constant process from alpha to 2. For these processes, we apply for each of them the corresponding equations, and for P1, V1, I think that here it's an error, but I cannot fix now. So this T2 should be here. Yes, not here, because it's T constant. This is T1 from 1, and, or it was supposed to mention T1 equal to T2. Okay, doesn't matter, we will see. So for the T constant process from P1 V1 to P alpha V alpha, yes, the first equality, but in the same time, in state alpha, we have reached the final pressure P2. So we can continue P2 V, the volume in alpha state. For the P constant process, isobaric process, we apply its law, its equation, so volume over temperature constant from state alpha to state 2, but in state 2 we have actually the volume V alpha over T1 there is a mistake, V alpha, T alpha, V 2 T2, so okay, I will see a little bit later. I do not see now what's the point. Why do we have V alpha again? All right, anyway, we express V alpha from here, from the first one, which will be the first expression with the last one. So we put together V1 and P1 over P2. And from here, V alpha will be V2, yes, and the ratio of the temperature T1 over T2. When we do the equality, we will have, and we separate the properties with the same, corresponding to the same state, we will get this PV over T, it's constant. So the form of the state equation that we used last time during the application. Now, why it's important the fact that we used the specific volume? The idea is that this constant now is actually the gas constant or specific constant of the gas that we denoted by R. Yes, this R, it's the specific constant. And as we have seen last time, it has particular value for each gas. Now, knowing this, replacing constant by air, we have the first equation, thermal equation of state expressed for 1 kilogram, PV equal to RT. This form can be also used further in order to get the differential form of this equation that is important for other processes, filling or evacuating space. We will see a little bit later. So the idea is that we apply a logarithm and then by differentiation we get this expression. Why it's important? Also because it gives variation in time of these parameters, the connection between them. Now, we introduce again the specific volume, or we use the specific volume that was previously introduced in deriving the second expression. So this specific volume, if it's replaced by its definition, the ratio of the volume over the mass, will convey to this form PV equal to mRT, which is the thermal equation for m kilogram of perfect gas. And the same differential form now, if the mass is not constant. Yes, you see, this is the difference between these two. When we use specific volume, the mass does not enter. But if we use the state equation for m kilograms and the mass varies as well, we also have to consider this term here. And this is the main general expression, differential expression of the thermal equation of state. And I just mentioned that, for example, the free exit of flue gases from internal combustion engine and uses this expression. And also we can say that in other order of ideas that this dm over m, which is expressed in dm over t, becomes, and dv over t becomes mass rates. Yes, mass and volume rates, which is the case for gas turbine, for pumps, for internal combustion engine. No, there we are working with mass. So there are the variation in time, which are called rates. And in this case, we can use the same equation, it's valid, but using rates, volume flow rates and mass flow rates as well. And all the other relation between quantities will remain the same. Now, just a small look on the normal state that we introduced last time. Let us say again that it is that we didn't mention at that time, we mentioned now. There are two normal states introduced, namely the physical one with the properties values that we considered last time, 760 millimeter mercury column, and 273.15 Kelvin with the subscript N. And what we call technical normal state with subscript 0 has the same pressure, but the temperature is in degrees centigrade. Why we are using two? Because the technical normal states was the first one considered historically. And there are a lot of characteristic curves. We will use some of them in the laboratory also that are represented for this technical normal state. So you have to know also its parameters, reference parameters. Now, what is very important for your applications is to understand, to well situate what means what one normal cubic meter. Of course, it's a cubic meter. Yes, it's a volume of a cubic meter, but under normal state conditions, which means that you will never be allowed to simplify one normal cubic meter with 1 cubic meter. Never, ever, because it's a huge mistake. Huge because it introduces errors, and from there away everything is wrong. So what you have to keep in mind is that everywhere where you find normal cubic meter connected to other properties, for example, you may have the density in the normal state. Yes, it will be kilogram per normal cubic meter, which is not the same with the density in another states, let's say state 1, which is expressed in kilogram per cubic meter. You are not allowed to do the sum of them, for example, because they are not the same. There are not the same conditions where they are expressed. So be careful. Also, the first homework you will have to use we have to keep to pay attention to this difference. All right, so I think that we will stop here because it's not worth to start the next law. If you have, maybe I will speak with Torben. Torben, you are with us?
Yes, I am.
Okay, so for the other, you are in the break, 10 minutes break. I will have a small discussion with Torben to clarify the situation. Thank you. So
Okay,
Torben, what?
Okay, thank you.
I answered you this morning very quickly, but what do you think to do finally? The idea is to follow 3 lectures in parallel.
No.
I don't think that you can handle it.
No. I can't do that. The first I already stopped to participate, so I just have 2 left. And there's also a German course of thermodynamics, but this is a little bit less hours per week. So I'm talking with my teacher in Germany if that would be enough for him, but he didn't decide it yet. So I hope he will decide tomorrow or today, and then I will see. Otherwise, there's also, I have to decide if I take this or the operations and supply chain management. It's the other I took. It's from another faculty.
Yes, so I understand that you want to follow some lecture from FIMA faculty.
Yes, yeah.
Okay, so what I did not understand from your message is why do you have to follow lectures in your university since you are an Erasmus student? There is a credit points equivalence for the whole semester if you come one semester to Polytechnic University. Is it?
Yeah, I don't follow the lectures there. It's just they have to accept it. It's how do you say it? 6 credit points in Germany, like ECTS.
Yes.
And the German course has just 4. So normally they say no, you can't do it because you do too less. That's why I did also the English course here with you, because I think it's 5 here with you, isn't it? It's a little bit more. I also checked the course description. You do a little bit more than the Germans. So I have to discuss this with my teacher in Germany.
Okay, so be careful. You can do this any change in the first 3 weeks.
Yeah, I know that. Yeah.
Okay, I am glad that you decided to participate today because we will have laboratory. So it's important to not miss laboratory. If you will decide that you don't want to follow the lecture, it's okay. You can quit next week. But in my opinion, of course, the choice is yours. The decision is yours. But in my opinion, it's quite difficult to follow 1 week one lecture and 1 week another lecture. So you will be a little bit stressed, to not say confused. And of course, it depends also on what expectation do you have from the grade point of view. But be reasonable. It's my advice. Okay.
Yeah. I think I will decide of these 2, but like for the weeks until I have to decide, like we have 3 weeks to decide, and I will try to do this week, and then I will have talk with my teacher in Germany, and I will see what I can do. It's okay.
It's okay for me. Just I kindly ask you to let me know what's your decision, okay? Because
so it's a little bit confusing.
Doesn't matter. No, it's not a problem. Just that I want to know what follows and how many students do I have to have. Okay. Break for you as well. Thank you.
Professor, I have a question.
Yes.
Which days we have a laboratory for this course? I don't know.
Mert, on Moodle platform, you have the schedule for lectures and applications and general, and you have also there the syllabus. Okay, so please read them carefully. You didn't participate to the first lecture. So every 2 weeks we have laboratories starting from week 2. Okay. And from week 1, 3, 5, 7 are applications. So the laboratory in our university, it's mandatory. So try at least, if you have other superposition of activities, to participate to the laboratory. Now, being Erasmus students, we will see if we can separate you on the 2 groups from 2 to 4 or 4 to 6. Okay? Until now, I saw that are 6 students, Erasmus students, but I don't think that all of them are participating. Actually, only you and Torben I see on the presence list. So this is it. Okay, so you may participate from 2 to 4 to not have this break from, okay.
Thank you.
All right. You are welcome. All right, can we continue?
Yes.
Yes.
All right, everyone is here more or less. Let us see. Yes, okay. So next law, yes, the Avogadro's one. What stated Avogadro? He made experiments at molecular level, if I can say like this, and stated that in two equal volumes containing different perfect gases, if they are at the same pressure and temperature, they contain the same number of molecules. Very interesting, this same number of molecules. We will see furthermore that actually not Avogadro's law is the most important, but the consequences of this law have application of interest. But until then, let us see the schematic representation of this law. So we have two gases, gas A, gas B, same volume, Va, same pressure, same temperature, we will have same number of molecules. Now, in order to speak about the consequences, we have to pass very quickly through a chemistry recapitulation, because we are using several properties and we have to speak the same language or to understand the same thing for this. So first of all, we speak about molecular mass. So be careful, it's not the molar mass, it's the molecular mass. And this molecular mass in chemistry was introduced as a non-dimensional number that shows the ratio between the mass of the molecule and the 12th parts of the molecule mass of carbon isotope 12. This is the way that this molecular mass was considered. But this molecular mass comes actually, if you go back a little bit to Mendeleev table, from the atomic mass. Yes, the atomic mass that we find there here passes to molecular mass, because a molecule has two atoms. So if the atomic mass of oxygen was 60, for the molecule we have double, as well as for nitrogen 40, and for the molecular mass we have 28. So from this we can continue furthermore with other examples, but these are, let's say, more usual, or you may have these values as atomic mass in your memory. Now, based on this, what is the kilomole? We have spoken last time about kilomole, but we did not enter in theoretical details regarding its definition. Actually, I cannot say it's quite a definition, but it expresses what represents this kilomole. So a quantity that is equal with the molecular mass, but expressed in kilogram, because 1 kilomole, so 1 kilomole of oxygen will be the equivalent of 32 kilogram, as well as for nitrogen, based on previous example. So what do you notice from this equality? That 1 kilomole is more powerful, I mean, includes much more quantity than kilogram. if 1 kilomole is the equivalent of 32 kilograms of oxygen compared to the mass of oxygen, 1 kilogram, for example, yes? The same for nitrogen. So you will see in further applications that when we will use kilomole, the data of kilomole will be very small, just because generally in thermal machines, you know, the quantities are not very high. In internal combustion engine, for example, yes, which is a closed cycle machine. All right, from kilomole, we pass further to molar mass, because we are using this very widely in our calculation. So the molar mass now comes and says that it's the equivalent in kilogram of 1 kilomole. So actually we pass in a way from kilomole to molar mass. We don't, actually the number remains the same, but the unit will become kilogram per kilomole. Yes, it's a way to express it. This would be an easiest way to the molar mass could be also differently expressed, but I do not want to enter in details, because it's not our aim now. The idea is to understand clearly what represents and what's the unit, because based on the unit we will try to show that you do not have to keep in mind all expressions. You can very easily derive them based on units. Okay, so we also mentioned that they are units of quantity, also kilomole, also kilogram. And with the molar mass, we can do the passage from one to the other one. Now the consequences. The first consequence regards the molar volume of gases, the molar volume. We found it in the short theory recap last week, but without introducing it in an appropriate way. Let us do it now. So we are going back to our two gases, A and B. Yes, both of them in volume A and in separate volume A and B. Now, when we look to the mass of gas A, based on the fact that this number of molecules N A and NB, if we multiply this number of molecules by the mass of one molecule, we can have the mass of the gas A and gas B. Yes? Now, furthermore, we do the ratio of these two masses using the previous expression, and here, in order to arrive to molecular mass and to molar mass after that, we just divide the mass of one molecule to 12 parts of mass of carbon isotope 12, of molecules of carbon isotope 12, and passing through molecular mass, yes, 32 for oxygen, and arriving to molar mass, the same, 32, but now in kilogram per kilomole, we can use directly this ratio of the molar mass of A over molar mass of B. You see here the number of molecules in gas A and B being equal, they will be simplified, and we arrive only to the ratio of the mass of one molecule of gas. Okay, this is one way. The other one is to divide the mass of each gas to its volume. So volume A, volume B, because this gives us the density. Yes, density of gas A and density of gas B, which will be, of course, different even if the two volumes are equals. That's why we can do this division, otherwise not. The density is actually the reverse of the specific volume. So here it's a small mistake. Yes, because here it was supposed to be VB over VA. Yes. Okay, I will correct and you will have the correct file uploaded after the lecture. So now when we take this result, MA over MB, with the reverse of this one, which is correct, VB over VA, we have got the product MAVA for gas A is equal to the same for gas B, which means that first consequence statement says that at same pressure and temperature, this product is the same for all perfect gases. Why for all? We have taken two different gases without any connection with properties or values or whatever, so they could be any perfect gas involved. So keep in mind this first consequence, the molar, actually this product, that we do not define yet what represents this product. It will come a little bit later, but it will be used later. Look, an example of what I called previously the use of units. Now, if we associate the units to the molar mass, kilogram per kilomole, and the units to the specific volume, cubic meter per kilogram, kilogram will disappear and we will have cubic meter per kilomole. So cubic meter per kilomole says us that it's a volume, but not a regular volume, but a molar volume because its unit is divided to kilomole. And we have got finally the statement expressed briefly in molar volume of gas A is equal to molar volume of gas B. So we can generalize for every perfect gas. So the molar volume is the same in the Avogadro's law conditions. All right, why it is important, this molar volume? Because in the normal, physical normal state conditions, this molar volume, you see Vm as notation, and the reference state is separately in the normal state. This is 22.414 for all perfect gases. And we have demonstrated last, or it was in the materials that were supplied for the first application, this value corresponding to the normal state conditions of the molar volume. So, second application, second consequence, regards the Avogadro's number. And based on the first consequence, yes, we may say that 1 kilomole of gas contains the same number of molecules, doesn't matter what gas we consider. And this number has the value that maybe some of you knows it, 6.023 10 to 26 molecule per kilomole. So if you use per mole, it will be 23, and it's the same as this one. If you use per kilomole, as we are using in thermodynamics, it's 10 to 26. Now, a good question is, how did Avogadro computed this number? Because this huge 10 to 26 molecules, it's something quite difficult to quantify one by one, yes? Will somebody dedicate some time to look to the Avogadro's experiments and to tell us next time how this number was derived?
I could do it.
Maria? Okay.
Yes.
Excellent. So in the beginning of the lecture, you will present briefly what you have found, okay? 5 minutes. Or I think that it's better in the beginning because we are continuing on the subject. All right, excellent. But remind me if I forget.
Of course.
Maria. All right, let me do the note here. Maria and Avogadro. Okay. So if we know this number, we can pass now to the universal gas constant presentation. It's the third consequence, and now you will understand also where from comes this, with a small demonstration, but very, very reduced. Namely, we go back to our two gases, gas A and gas B, under the same pressure and temperature conditions. And when we apply the first equation that we have introduced for 1 kilogram of gas, it will be PV, small v volume, specific volume, equal, be careful, it's the specific constant, if we work in specific volume, multiplied by the temperature. Same for gas B. Yes. Now, when we want to derive something, we are allowed to multiply or to divide, as you have seen for the first consequences, with same property or equal properties in both sides. So in this case, because we have some idea about what this universal constant, how it's related to the specific constant, we can multiply by the molar mass, left and right. In this way, we create here this product that will represent specific volume multiplied by the molar mass, will represent the molar volume of gas A, and the same for gas B. We didn't modify the right side of each equations because, for instance, we have no idea of what it could represent. But taking into account consequence number 1, the molar volume of all perfect gases are the same, yes, in Avogadro's law conditions, which means that we have PA equal to PB equal to P, the temperature equals to T, and the molar volume equals from C1, we will have this term equal to this term and temperature TA to TB. So when we do the ratio of the two equations, we will get only the product MR, the molar mass, and the specific constant for the two gases equals. And this convey to the idea of this product representing the universal constant. And the notation that we are using in thermodynamics are M instead of R that was used until now, 8,314.3 joule per kilomole Kelvin. Now, this is the mathematical connection to to the specific constant. But let me tell you that this value was not derived based on this expression, because actually this expression will be used to determine the specific constant. But you will wonder now why this universal constant, besides the fact that it's the third consequence, is present here. This value was determined by the product of Avogadro's number and a constant that is called Boltzmann constant, and it is 1.38 10 to 23 minus 23, which if you do the calculation, you will get this value. So you see, the thermodynamics, actually, it's a science that was created mainly based on experiments. And then the theory came and explained or put in the basis, the theoretical basis for the experiments. But that's why it's important to have in mind that experiments are quite useful, and also sometimes, as it was for first law and second law, they can be also stated as general laws. Now, this is the expression that we used last time, the specific constant of the gas being the ratio between the universal constant, which in thermodynamics belongs also to molar family, due to the fact that is divided to kilomole here, and the molar mass with the unit joule per kilogram Kelvin, and with the specification that it has a different value for each gas. That's why it's called gas constant or specific constant. All right, it was also a part that I did not edit, thinking that it will be too much information, but we will continue next week with the state equation to finish, to present all forms, and some other remarks. And then we will pass to the mixture. So let me take advantage of this short time that we have to speak a little bit with you, because I cannot use the breaks to do this. And it's important to establish some issues. First of all, if you have questions for what was presented until now, I hope that it explained or it completed what was introduced in the application last week, the thermal state equation applications. If you have solved the problem and you have some question mark, we can also discuss, or if something was not clear now, maybe go back and try to explain differently. Until you will think, yes.
Can we already upload the first quiz?
No. You have to look before the next lecture. You have 2 weeks for each one. Yes. So before the lecture next Tuesday, you will find on Moodle platform the students that have to upload the quiz 1. Okay. Not everyone. Just who has the chance.
So one homework is
no, it's not homework. It's not homework. There are different activities. Yes, you have quizzes, which represents the application during session problems. These are called quizzes. What remains to finish at home, if it's the case, if we have no time to do together. And homeworks will be given according to the schedule in the table. The first one in week 4, and be careful that it is due on week 7 or 8. I think 8. Yes, so in this table, sorry,
is every 2 weeks.
The quizzes are every 2 weeks.
Okay.
Okay, and just take the information. Who has to present? Maybe I will put it on Monday, because on Tuesday you have already a lecture before. So be careful to the time scheduling, but you cannot, you do not have much time. I mean, you do not have time to finish the quiz before knowing that you have to upload it. This is the idea. That's why it's a limited available time to upload the quiz, okay? All right, let me go back to this question mark that I have here. Sometimes my brain is a little bit lost. So maybe you had the explanation by yourself. This equality that I did not find a connection with V alpha over T1 actually comes from the first ratio, because the temperature T alpha, it's on the same isothermal line, it's T1. I looked on the volumes and I didn't realize that actually the temperature is the key in this case. So it's correct, this equality is correct, and this is the explanation, the fact that in alpha we have the same temperature T1. But it still remains to modify this curve that I don't know why he moved a little bit to the right. So I cannot do this now. I have to pass in another file, and this is it. All right, other questions? Everything was so clear. I can't believe. Or it was too fast. You have to tell me. If you understand what I am speaking, if the way I'm speaking, if I don't know, the rhythm is too high, if I have to insist more on some issue, if I have to write more in more text in what I have presenting. But the idea is that if I'm writing everything down, I will not have from what to have questions for theory. So that's why I advised you to take also notes sometimes when I'm emphasizing something, because I think that what I'm emphasizing is important, and of course, if it's important, you are supposed to remain with this in your mind, in your memory, and that's why the question, the theory question, the exam could be from these parts. It's my logical approach. Now, what do you think could be different? So, don't hesitate to give me a suggestion. It's just someone said that actually you are not learning from me, but we are learning from each other. So let's make dynamic this process. Don't be afraid to suggest what you think that could enhance the comprehensibility of the lecture. If not today, maybe in the weeks that comes. It's mandatory to be today. Just that I have another issue to discuss with you. Namely, it was suggested, actually it's not a suggestion, it's something that we have to do. Alex and Andra.
Yes.
Alex was here, Andra.
My name is Andrei. Actually, Alexandru is my last name.
Oh, excuse me. Yes, you are right. Okay, until I will become familiar. Andrei and Andra is here. Okay, so we are asked to establish a regular meeting with the students in order to maybe not only for science, but also for other problems that you may have, and we can help you. And the idea is that I am also your advisor, the group advisor. So can you choose, depending on your schedule, 1 hour that where we can meet, all of us? I mean, all the group. I saw that you have
E un fel ca oră de dirigenție, cum făceam în
yes,
liceu.
yes, something like that. I think I don't know what's in mind of the dean, but I received this message from the dean, but it's valid for for the university, not only for faculties. So this is it. We experience together. I have no idea, but I have to mention this this moment, and I will put in on Moodle. I will be available, and if you have any question for quizzes, for lecture, for I don't know what is related to thermodynamics, we can discuss during this hour. It is not mandatory to be connected, all of you, I think, but you have to know that you have this opportunity to share, to change ideas, or to ask for explanations. So, yes.
Professor, I have a question.
Yes, Matt.
In the model, there is a laboratory document. Do we have to send you in this week, or the another lessons?
Okay, so for the laboratory, I thought that I will discuss on laboratory, but let us do it now because we have time. The laboratory, at least during the first months, yes, it's online. It's not a huge problem for us because the first 2 laboratories in week 2 and week 4 are with presentation of pressure and temperature methods and instruments, measurement methods and instruments, okay? I tried to show you as much as I could from the pictures on some video, just to more than I could have presented in our laboratory. So this one aims to introduce you to have an idea about the method behind the instrument, and also how to use these instruments in the idea that you will find some of them in the experiments that we will do together. So briefly, for the first 2 laboratory, you don't have to upload anything, okay?
Okay.
Because you will have at the end, if you look in the syllabus, you have in the last application, in the last week, you have there a small laboratory exam. So you will have a question from pressure measurement, you will have a question on temperature measurement, and this will be part of the grade for laboratory. The other part will be, if I cannot say now because I do not know if I'm wrong or right, how will be for the other 3 laboratories with experiments. if the situation will be bad as it is in this moment, and we will not be able to attend the laboratory, the university, in this case, I will try even to record the experiments and to share it with you and to give you, yes?
When do we have the test?
The test in the last week, in January.
Semesters, okay.
Last week,
The
week
exam
14.
or the partial?
No, we are not speaking. We are speaking now about the table with applications, yes? And in the table with application on last week, you have flows through nozzle with friction and laboratory exam. Am I right? Alex Razvan? Have you checked on Moodle?
Yeah, I checked on Moodle, but I didn't fully understand. That's why I
Okay,
asked.
so this is the explanation now. Okay, that's why I thought that it's clear enough. But if you have questions, of course, that we discuss them. So now it's clear for everyone. What is the test? The test is during the lecture, and it will be like reduced, if I can say, exam, containing some question of theory and an application. And this will be explained when we will get closer to this, okay? Week 8, it's far away from now, so let us concentrate to accumulate knowledges until then. But for the laboratory, Mert is right, we have to know how it works. So, going back to the laboratory, for the next 3 laboratories, week 2, 4, 6, 8, and 10, it is marked in the syllabus. Report is due on week 2 week after, yes? And also on Moodle platform, for when I will put the materials support for this laboratory, I put in parentheses the deadline for the report. Now, if for quizzes, I do not collect all of them, but I hope that all of you will do, because you will not know what students has to upload the quiz. For the reports, I need all of them in order to give you this the grade for the laboratory. And week 12, we have a combined laboratory and session problem, because I found that this vortex tube rank Hilsch, it's quite interesting for you as an application to second law. And I think that you can see more on what I will present than doing the experiment, because there you will see only the fact that on one side comes out hot air and on the other cold air. All others are calculations, so I'm not really interested. There are a little bit too long or too heavy calculations, and that's why I wanted to simplify, to show you the idea, to show you the principle, and to do only entropy variation calculation, to show that it is what's happened inside. It's an irreversible process. And that's why there you won't have to, it will be actually quizzes with a part of laboratory, but without experiment. So in this way, we equilibrate a little bit laboratory with application, I think. So this is for laboratory, to understand what means there, what means report. So the report supposes to do calculation based on the recorded data. Now for the recorded data, we will speak a little bit later when we will arrive to the 3rd laboratory. Until then, there are 2 laboratories with presentation. You have maybe to complete with your own notes during the presentation. Again, as for lecture, I'm not writing quite everything, so you can take notes on what is not written on the files. And some of comments, of course, are extra presentation, and these are also important. So if you want to take notes, you will have the whole information. If not, this is it. The idea is that until the lab exam at the end of the semester, you will forget, of course, some comments. So that's why I advise you to take notes on these comments. There are common sense, technical common sense, but some of you can have this information, some of you not, so, or the logic of the process, and this is it. All right, so we made a little bit clearer the application part. For the lecture, you have for each, and I will try to be in time, because we are losing this 1st December week lecture and application, and everything is now concentrated on the lecture that remains. So you have for each lecture what more or less will contain, not everything, but the main ideas, and the presence of this test in week 8. Also be careful, I will, of course, also for the homeworks, when they will be given, they will have mentioned in parentheses the deadline. And for the deadline, you will have to be careful to the timing of this when you can upload them. So actually everything is on Moodle, just that you have to look from time to time what is new or what is old, but you didn't pay attention at the moment they were uploaded. Okay? But of course, again, if you have questions anytime, even if you cannot connect to a team platform during this schedule of meetings that I'm waiting from Andrei and Andra, you can ask questions using my email, as the Erasmus students did already. So I am in the list of participants with the address, so you can write me a message and I will answer you. Other question or problems that you may have? Okay, on the syllabus, just because we are discussing about it, there is 10 extra points, yes. I explained last time, maybe it is better to say again, that if you want to enhance or to assure that in the limit of 1 point you can have a better grade for this course, I give this opportunity if you answer to the questions during the course, during the application. Everything will be quantified and will enter in this maximum 1 point extra to the grade. So actually you can start from 11. And my advice is to pay attention to the semester activity, quizzes, laboratory reports and homeworks, to the deadlines, in order to not lose points. And the idea is that working quiet at home and not under stress at the exam, even if it's still at work. I don't know actually how it will be until then, but the idea is that what you can get by your own forces and with all materials in front of you, you have to take advantage of it and to try to get the maximum of this. All right, so Andre and Andra, have you agreed? And can you propose me a day and time?
Not quite.
Not quite. So I will let the break, but you are not participating to the same laboratory.
Yes,
So-
I'm from 4.
So I will let the break, and maybe after that, when we will meet again from 2 with Andre and from 4 with Andra, I will have a common answer. Okay?
Can't both groups do the lab in the same time?
Normally not. So you have. Actually, I do not know the separation of the groups, how it is done alphabetically. The first part, yes, 11. Do you have 11
it's
students?
not alphabetical. It's group A and group B, and who wants at group A comes at A, and who wants at B goes at B.
Really? And how can I know this?
We should have a list.
Okay, and can you provide somehow this list?
I will search for it and see.
Sorry?
I will search for it.
Okay, okay. So when we start the laboratory, just to have a small idea of what's happening, it's true that being online for you it's not convenient, but I have to justify the 2 hours, unfortunately. This is it. So as we are recording, even if I will say the same thing, this is it. It's group A from 2 and group B from 4. No, yes, I said okay. And for the Erasmus students, as only Merz and Torben are present, if they want, they can participate from 2, and they will remain like this. And the others, when they will reach us, we will decide to separate them into groups, or as they want.
Professor,
So,
sorry, the last week I couldn't participate the course because of the mobility. Did you attend? Did you attend for course?
yes, I will put them in. I will try a way to make available either in one cloud where you have access, either to give you the link to download the record and to make it available. Okay, but for instance, I do not have much time to do this, but I will do it. Okay.
Okay, thank you.
So we stop here, and you have 10 minutes break, and then we will meet with the first group, group A, for the first laboratory, and from 4 with group B. Waiting for this meeting scheduled given by Andre and Andra. Thank you very much for your attention, and see you later.
Thank
See
you.
you. Meeting
Bye-bye.
you later. Bye
Okay,
bye.
thank you. Bye bye.
Thank you.
See you later.
Bye.